In a circus performance,
I'm going to stop you for a second. This is my favorite. In a circus performance, now we can do whatever we want. Go ahead.
In a circus performance, a monkey on a sled is
A monkey on a sled. Perfect.
given an initial speed of 4.0 meters per second up a 25-degree incline. The combined mass of the monkey and the sled is 20.0 kilograms, and the coefficient of kinetic friction between the sled and the incline is 0.20. How far up the incline does the sled move?
So we have a monkey on a sled. We have an incline. We know the initial velocity of the monkey up the incline. We know the mass of the monkey. We know the coefficient of kinetic friction between the monkey and the sled. So we've got the monkey on a sled. We have a sled. We have a monkey. Going up the incline, we're looking for delta D parallel equals question mark. It's going to end somewhere up there. We have some sort of angle. Let's see. Class, is there friction?
Yes.
Could we draw a free body diagram and sum the forces, figure out the acceleration?
Yes.
Are we going to do it that way? No, why would we do that? We are instead going to use the work due to friction equals the change in mechanical energy. In other words, the force of kinetic friction multiplied by the displacement times the cosine of theta equals the mechanical energy final minus mechanical energy initial. Before we can use this equation, what do we first need to do, Janine?
We need to draw the initial and the final point and the zero line.
So we'll put the initial point down here at the bottom where the monkey starts, the final point up at the top, and we'll put the zero line such that right where the monkey starts, so it's at the initial point. Starting on the far right, list the three types of mechanical energies, Avi, and tell me which ones are or are not there.
There's no elastic potential energy, no spring. There's no gravitational potential energy because the height initial is 0.
Good.
And there is a kinetic initial.
Because initially
There's 4 meters per second.
we have some sort of initial velocity, which is 4 meters per second. Finally, Andrew, what sort of energy does the monkey on the sled end with?
Well, there's no elastic potential energy.
No spring.
There's no spring. There is gravitational potential energy because it's above the zero line.
Good.
And there's no kinetic energy because it comes around.
We're figuring out the maximum height, so that's going to be, or the maximum displacement, so that's going to be where he stops briefly. So M, G, H, final. Okay, left-hand side, we have force of kinetic friction, D cosine of theta. Isha, what do you want to do with that?
We can break the force of kinetic friction up into UK times force.
Ever since I bring up breaking things into components, people always say break things into this, but this is, we're just substituting in the equation. There's no breaking here if these are components, but we have a habit of doing that. So just realize that's the equation for the force of kinetic friction. I agree with that. We know D is the displacement, which we're looking for. We'll just identify that as delta D parallel, and we have the cosine of our angle. All right, from left to right, class, do we know the coefficient of kinetic friction?
Yeah.
Do we know the force normal? No, we don't know that. Do we know the displacement in the parallel direction? No, so we have two things we don't know. Cosine, do we know the theta? Do we know the mass? Acceleration due to gravity?
Yes.
Height final. So we don't know height final. We don't know the displacement in the parallel direction. We don't know force normal.
Yep.
Mass? Do we know it? Yes, and velocity initial. Okay, so we have three things in here we do not know. Chandler, what do you want to do?
Well, we can sum the forces to find the force normal.
We do need to figure out the force normal. Before we can sum the forces, we need to first what, Michael?
Draw a free body diagram.
Draw a free body diagram. Here we have the monkey on the sled. We'll put it kind of halfway up here so we can draw the free body diagram. Actually, that's not going to work because it's going to be kind of in the way. Let's draw the free body diagram. Let's just do it right here so we can see everything in our free body diagram, else we're going to lose parts of it. So, free body diagram, please.
Gravity parallel down, or perpendicular down,
I got lost. You said force of gravity.
perpendicular down,
Am I doing the force of gravity parallel or perpendicular?
perpendicular.
All right, so I'm going with force of gravity perpendicular, perpendicular, and down.
Yeah.
Okay.
And then force normal perpendicular up, force of friction parallel to the flat.
What kind?
Kinetic. And force of gravity parallel with a lot.
And parallel to the equal. We're trying to figure out the force normal, please, from here. Jeremy?
So the sum of forces equals force normal minus force of gravity perpendicular, and that equals mass times acceleration. And the acceleration in the y direction, y, perpendicular, and that equals 0. So then the force normal equals the force of gravity perpendicular, which equals mg. Cosine theta.
So we have now the force normal equals mg cosine theta. We could substitute back into our equation. We get mu k times mg cosine theta times delta d parallel times the cosine of theta equals mg h final minus 1/2 mv initial squared.
Do something in common.
Rebecca?
Everybody brought mass party.
Thank you. We can be equitable. We can take mass from everyone. So we have mu k times g times a cosine of theta times delta d parallel times a cosine of theta equals g h final minus 1/2 v final squared, or v initial squared. Let's see. So we know the only thing we don't know here. There are two actually. Delta d parallel. We still don't know the height final. Jennifer, any thoughts? Height final?
I don't know.
Bianca?
Use the.
Oh. Jennifer wants to come back in.
Can we use sine?
We could identify that this is our height final. This is theta and delta d parallel. So go ahead, Jennifer.
Okay. Sine theta equals opposite over hypotenuse.
What is opposite theta?
Height final.
Delta. What's height on the hypotenuse?
Delta d parallel.
Delta d parallel. In other words, height final is equal to delta d parallel times the sine of theta. So we can now substitute that into our equation. Mu k times g times a cosine of theta times delta d parallel times the cosine of theta equals g times delta d parallel times the sine of theta minus 1/2 velocity initial squared. At this time, why don't we plug in some numbers? Paige, why don't you give me all the numbers here, from left to right. Mu k.
Mu k is 0.20,
G.
positive 9.8,
Good. Cosine of what angle?
the 20 degrees.
Times delta d
25
parallel.
degrees, sorry.
Is it 25? Okay.
Yeah.
Times 25 degrees times delta d parallel, which we're looking for, delta d parallel, times the cosine of
180,
180 degrees equals G
positive 9.8,
delta d parallel, which we're solving for, times the sine of
25 degrees,
minus 1/2 times velocity initial.
4.0.
4 squared. So notice, you have to be very careful to pay attention to where your angles came from, because we have theta of 25 degrees, theta of 180 degrees, and theta of 25 degrees. This cosine theta right here came from the force of gravity perpendicular, so that is the incline angle. This cosine theta right here came from the work equation, which is the angle between the force of kinetic friction and the displacement, which we've already identified as 180 degrees. And this sine of theta right here came from the SOHCAHTOA we use for the height final. So very nice. Let's All right, let's get some numbers here. I think at this point, sometimes it's easier. So can I have all of this right here? 0.2 times 9.8 times the cosine of 25, please?
1.78, 1.7764.
1.7764. Notice that's a negative number because the cosine of 180 degrees is a -1. So we have that number in front of delta D parallel. 9.8 times the sine of 25, please.
Was that?
9.8 times sine of 25.
4.14166.
That's multiplied by delta D parallel. And then 1/2 of 4 squared is going to be 8. So, help me solve for delta D parallel, please. Yeah.
You can add the 1.7764 to the other side.
Okay, when we do that, we get 0 equals 4.14166 times delta D parallel plus 1.7764 times delta D parallel minus 8.
And then you can add 8 to the other side and then combine the delta D.
If I add 8 to the other side, we get 8 equals 4.14166 times delta D parallel plus 1.7764 times delta D parallel. Students tend to get scared. I don't know why. Realize we could just pull out the delta D parallel, right? This is the same thing as delta D parallel multiplied by 4.14166 plus 1.7764. Somehow having all those numbers gets scary, but it's not. It's just numbers. Numbers are easy. Delta D parallel then is equal to 8 divided by these numbers, 4.14166 plus 1.7764.
1.35479.
With sig figs, 0.20, is that 2? Is that correct? In the givens? Which is down to 2?
Yeah.
Okay, so we get 1.4 meters. The displacement of the monkey on the sled up the incline at the circus.